how to make recommenders work better. Make some recommendations. These are very personal recommendations of my own based on my own limited experience. And so they're probably not correct in all cases, but they are tried and proven in real applications, and so they should have some weight. So what I'm going to talk about tonight is some general thoughts about what we're doing with recommenders, a little bit of architecture of the sort of recommender that I'm talking about generally, and then a slightly controversial point, and that is I really feel like the algorithm that you use for recommendation, the exact algorithm, whether it's decomposition, whether you use certain kind of regularization, whether you use co-occurrence, things like that, I think that matters almost least among all the tasks you will do in building a real recommender. And that choosing something that's pretty good quickly is going to be one of your better choices, and then do the stuff that's really important. And the really important stuff is the stuff I'll talk to you about next. And that includes driving the exploration of the users in whatever universe you're making these recommendations. I want to talk about how to drive that and what issues that raises in there and how to solve those using meta-learning. You can contact me. There's an email address, there's a Twitter address, there's another Twitter address, there's a subscription address from Mahout. We love new people to come in and talk. One of the things that Mahout's best at is recommendations. It has a wide variety of implementations, and it has a history of doing quite well in practical situations. I'll have those slides uploaded. Clearly they have a way of doing it with the Recommender Stammtisch as well. Here's some hashtags, in case you feel the urge. So what I think of as recommendation is a little bit different than what a lot of people think. I think that the best way to think of recommendation is we observe some behavior, possibly many kinds of behavior, and we want to encourage the behavior. You know, I just kind of subtly move the beer closer to her, just to encourage things. Yeah, it's a good recommendation. It was based on past behavior. She put the beer on the table. So I just encourage it. So that's what we want to do with recommendations. Sometimes very subtly, sometimes not. Sometimes we tell people what we're doing, sometimes we don't. Sometimes we put up a most popular page that is actually weak recommendations. It is popular things, but it's the idea that matching the user's rating was the goal. And we have a technical term for this. This is called bullshit. The real goal is to get her to drink her beer. To encourage some behavior. We really don't care if we get exactly the correct rating, and especially we don't care if we get exactly the correct rating on things people don't like, that we're never going to show them. If we say this is the last item, and this is the next to last item, and we got them in the wrong order, who cares? It's just irrelevant to what we're doing. What we want is to cause behavior. If we do that, we're done, regardless. And so we want to optimize for that, not optimize for observed error in some rating scheme or something like that. So there's many examples of this. People have seen these books and videos and music and everything else. But you also have some much more subtle examples. A friend of mine showed me last night or the night before, I forget which, it's all blurring together, it's Berlin. And so he showed me, he works in Google Maps, or he did for many years, works in a different section now. But the next version of Google Maps, which is all vectorized and things like that, does real-time recommendations based on what you're hovering over with the mouse. And so the map is trying to guess what you're looking for. And so if you hover over an U-Bahn station, it shows you U-Bahn schedules and tracks. And in particular highlights the single line that you seem to be interested in. If you clicked and searched a little bit ago for a particular kind of restaurant, it will make recommendations, and so what he calls the measles, the incredible number of restaurants on there, only a few of which are shown large, they will pick which ones they show you the details for to match your apparent tastes. And so it's a great example of a very subtle recommendation engine which is tuning the information you see. There's far, far too much information for you to understand there. They can't print it all. You wouldn't be able to read any of it. So they have to choose. So they now choose to try to show you the data you'd like to see and to facilitate the task in your mind. So they're suggesting behavior, and then they're trying to do that. Also, I built these, I know other people build these, automatically self-structuring websites where all of the navigation is based on recommendation sort of things, and where you might go to one secondary page or another depending on which seems to be performing well based on who you are. This is a very powerful technique, but it doesn't look like recommendations, it looks like links. It looks like the page. But in fact, there's behavior being recommended there. Now, my own preference is to build very, very simple recommenders. I think that they're the most effective for me, partly because I get bored when I try to build this algorithm for 2 years at a time. But it's also very important in the world I live in, which is startups, to get a minimally viable project immediately. If I can accelerate this by 2 months, that's 2 months I have to get ahead of competition. And this makes a big, big difference when you're trying to get mind share, when you're trying to succeed ahead of others. And so getting that out the door sooner and then optimizing is really, really important. And so what I want to do in general is build a system like this. Look at the entire history of interactions. Some are quite rare. Some have history buried deep in the past. Some are quite current and novel. I look at co-occurrence, and then I use these where there is anomalous co-occurrence as indicators. And then I put the indicators directly in a search engine. The search engine is searched via queries, which are themselves behaviors. These are not textual searches, and this is not textual data I'm searching. Although it might include geolocation, it might include a little bit of textual information, but the search engine gives me huge flexibility. Look at the history. Notice user 1 did thing 3, and user 1 also did thing 1. So we can put it into a user history matrix like this. We can then do co-occurrence, which is the easiest said in a matrix form. And note, sadly, in rumping relative to the previous speaker, you really can't do this online. And the reason is because if you use a robust co-occurrence detector, then the first coincidence that you observe has very, very low rate. It's just a coincidence after all. So it will be thrown out of the co-occurrence matrix if you have any limited capacity at all. That means that you won't, when you see the second co-occurrence, it'll look like the first. Alternatively, if you use co-occurrence and correlation directly, the 100% correlation you get the first time you see it looks like a very high score, and so all the singletons go into the table and they crowd out anything with higher frequencies. Either way, there's so much possible data that it's very difficult to keep it into any online finite structure. So you do have to run very large analyses to find these. You can adjust them in real time, but you can't find the long tail sorts of things you need. So you have to do something like this. Now, a lot of people, when they first started building recommenders, they did the users who did X, or H in this case, also did this other thing. A, the history matrix, would transform the things they did into the users who also did that. And then A transpose would transform that back into things. This is sometimes called user-centric, where we find similar users. But we can factor that out, move the parentheses. Now we have a large offline computation of a very stable data product. We can do it batch-wise, daily or weekly. You can do that in a number of different ways, but it's an offline process. And then the online process is just that last multiplication. And so what we do is we take co-occurrence and we filter it to find anomalous co-occurrence. And that gives us, for instance, in the case of that 2, we can say, yes, those 2 occurred 2 times together. They occurred each of them once in other contexts. And we have very little data because it's a toy example that has to fit on one slide. and we can build a score. I'm not going to go into details here, but there are better scores than correlation, which find, so here, for instance, we have unique co-occurrence of A and B out of 3 things. Correlation would say 100%. It would say 100% here as well. But this one, where they only occurred together, never occurred apart, out of 10,000 instances, which says they're both quite rare, that's an interesting almost case. This is an uninteresting case. And here, where we looks like we have a correlation, an overabundance of 1.3% is against 1%, that would have a moderately high correlation as well, but it's absolutely nothing. In this case, where we have 10 occurrences out of 100 only together, this score shows that as a very high-ranking thing. We can look at these as roughly standard deviations. So 7 standard deviations is 1 out of 10 million sort of things. This is called log likelihood ratio, and it can help us quantize this thing. Okay? And then once we've quantized that, we can put each row into a search engine as what I call indicators. The non-zero elements become elements of a search engine. Okay, fine. That's cool. I've built machines like that. Other people have built things like this. Mahout implements it very easily, and it's very simple to deploy because you're just deploying a search engine. It's very, very well-established technology, very stable code. But we can do a lot better. We can still do it in the same thing. We can integrate multiple kinds of behavior. The point is coming soon, I promise. We can even look at not just different types, but different actions, and doing that same mathematical formula, we can combine them into a normal recommendation. It makes horrible noises quite well, but not me. So we have a normal recommendation here, and we have what I call a cross recommendation here, so that we're taking the second kind of behavior and we're making the first kind of recommendations. But this works the same way. The same LMO scores work, the same sort of search engine deployment. Cross recommendation is an interesting capability. It's a special case here. Okay, this is wonderful. So we now have a technology we can build a recommendation engine. But I'm moving fast because the exact algorithms don't matter so much. Now we talk about why. The real issues are exploration. That means, does the system suggest things that it doesn't really understand? Does it spend a little bit of relevance today in order to get better data to make better recommendations tomorrow? Or does it just tell you what it definitely knows? If it only shows you what it definitely knows, it will learn more about what it definitely knows, but it already knew that. This is similar to the problem of when you're trying to build a better search engine. If you look at the things people click on, and when they search for tiger, and then they click on an American football or baseball team or something like that, then you say, ah, that's even more tiger than I thought it was. And so you boost that document. And so you learn that that document has tiger in it. But you knew that document had tiger in it. So what's the point of learning that? So this sort of narrow learning, where you only show what you're certain of, you only learn about that, you only learn from that, you only reinforce the knowledge you have. And the search engine or the recommendation engine becomes more and more narrow and less useful. Instead, we want the search engine, we want the recommendation engine to explore, to try new things a little bit. And how big a little bit is a key question. We also want to make sure that results have diversity. Most of the ordinary sort of literature about recommendation talks about maximizing the probability of an individual item in a recommendation list or across the bottom of the page or something like that. But the individual item is not what we're recommending. We're recommending a portfolio of items. And if we recommend the same thing to you, or identical enough things to you 10 times, it doesn't increase the probability you'll like it. If you like one, fine, you'll like all of them. If you dislike one, you will dislike all of them and the recommendation engine will lose. So if we show you one kind of thing, maybe twice, maybe 3 times, and then a very different kind of thing, then if you don't like the first one, we get a chance to find out if you like the second one, the second kind of thing. And so diversity in the recommendation engine is a very, very important thing. Because we're not making single recommendations, we're making a bunch of them. These are 2 very, very important issues. The third one is speed, and this is the most disappointing of all to an academic, like I used to be. And you find out that if you could decrease the recommendation time from 150 milliseconds to 10 milliseconds, you can probably increase the lift by 10 to 20%. That's disappointing. But that means we need to go for simple engines again and optimize based on gathering better data. And the last few percent of a recommendation algorithm's performance is not the issue. The issue is gathering better data and doing it quickly and getting the diversity. So the real problem here with gathering better data is what I call the second page effect. And if you look at the click-through rate of any normal system, this is simulated data, just to show the shape of these things. If you look at the click-through rate, I'm standing behind that, and it's just adapting me away. So if you look at the click-through rate as a function of the rank on a search engine page, it declines precipitously. The first few items have high click-through almost regardless of how relevant they are. If those were all equally relevant, the top items would have higher click-through, partly because the lower items would not get clicked if the first item got clicked. The person would no longer be there, no longer be looking for what they want. But the horrible thing happens at the end of the first page. Only a very few percent of the people, unless they're kind of a crazy sort of user, will ever click to the second page. Mostly, if you don't show them something good on the first page, they say, idiot, and they go do something else. Maybe they use Bing instead of your engine, or whatever. But people are not very patient. They try to reformulate the query, they do whatever. And so if you have an answer that is consistently here, you will learn nothing about it, to a very close approximation, unless you have 100 times more data than you need. You will learn nothing about it, even though it's just below the edge, just barely too low. And so the search engine, the recommendation engine, that only learns about what it knows, this first page, will never learn about that 21st item. It's a big problem. And one of the easy ways to fix that is something called dithering. And so if we look at these numbers, they started out in order. And then I added a certain sort of increasing size noise to them, which is self-similarly so that the 1 through 3 would be reordered just as much as 10 through 30, which would be reordered just as much as 100 through 300. Now I did this just a few moments ago on the table, so it's kind of a sloppy job. But if you look, 1, 2, and 3 are very much near the front, and then 4 and 5, and 6 and 7, so on. I should have highlighted 24 and 34 and 28 and 32 all appear on the first page, because they were raised by this noise into the first page. And so if an algorithm were trying to recommend numbers and it thought maybe you like numbers more than 20, you can imagine that this is metaphorical. The first line there is the first 20 numbers, and now you've got a chance to look at number 24, number 34. And you would never have had a chance because you're probably not the sort of person, I can just say this from first principles, you're probably not the kind of person to look at the next page, the next line. And it can do this for some people some ways and some people a different way. In fact, it's very handy to use time rounded down to say 5 minutes or 10 minutes, quantized as your seed, so that the results stay stable for a few minutes, so people trust you, and then they change, which they interpret as, oh, there's new stuff. There's new. And I'll come back because it's always got new stuff for me. Well, I do have new stuff. I have stuff from the second page, which you would never have looked at. And so I just conned you into coming back and looking because there's new stuff. It's always new. It's always accurate because it's stable for a little while, and then it changes. So what we can do with this is we stimulate both people to come back because there's this sense of novelty. It's not like the game is over the first time you look at this page. They can come back and look at it. And we've weakened the boundary of the second page. But there's a real big problem with this, is we started out by ranking these in the best order we know. And then I added noise, which brings the things which were very low, which we thought were very bad, up to the top. And I've taken things that we thought were very good, that were at the top, and put them down lower. So these results will be, if our recommendation engine has any sense at all, these results will be worse than the unsorted results. I'm making them worse on purpose in order to weaken the second page effect, in order to get people to come back, in order to gather more and better data. This is an investment, not a foolish idiot thing to do. So I make it worse now in order to make it better tomorrow. Because I will learn more about a broader range of things, I will learn about the things that were on the second page that were grand ideas. Now, there's a real question about how much of this we do. Now, the way I picked how much of this I would like to do is I sat there and I tried it 5 or 10 different times with different settings so that it would be aesthetically appealing. I wanted number 1 to be first, to make the point that they stay in order, and I wanted several things below that to be on the first page. But that's not really an acceptable way to design a real system. That's okay to design one slide. So we have to decide how much of the noise we add. And we can't say that the right amount, slides are out of order here. So for instance, here's the equation I used. I said the rank plus 20 times the exponential of r divided by 20, also times a uniform random number. Now there's constants there, magic numbers. 20 and 20, well, they happen to be the same, but they didn't start the same. I started with 5 as the left 20. I just kept goosing it up until it made it move around a lot. I tried 50, oh, it's way too much. So I just made it pretty. I had 2 numbers I'm adjusting there. There's another thing that we want to do, is we want to do anti-flood. This is the portfolio thing. The way that to do anti-flood is you look at the results and you say, are they very similar to things I've already shown? I have a limited tolerance for that. Once I get down to 2 or 3 of the same thing, or nearly the same thing, from the same publisher, the same words, I push those down. And that allows different things to appear on that first page. And how much do I suppress these things? How similar do the items have to be until I suppress them? So I have several knobs to tune there. And so we've got these knobs, and we've got the hyperparameters for anti-flood. How can we learn what the knobs should be? I've taken a very simple recommender algorithm that has no knobs, and suddenly we have more knobs. And these are the most important knobs in the system. The recommender algorithm is pretty good. You know, it's usually in the top 3 when people evaluate these things, at least on ordering. But these are why it can be among the best. So, what I want to do is I have 15 versions of the landing page, or I have 100 different knob settings. How am I going to learn that? And I would like to take a quick diversion. Some people have seen this. There's a coin. You think, you thought you would know what would happen. You don't, because I'm not going to flip a coin. I'm going to flip a beer bottle top. Okay, I know which one is heads. You don't. So if I flip it, what's the probability of heads? It's what? Why 50%? The what?
Right now it's not 0.
No, right now, before I flip it, what's the probability of it coming up heads? Why?
Unless you can switch the heads around.
Well, of course I can do that. But you can trust me today. You can't usually trust me. But if I'm going to flip it, well, there's a very simple reason, very, very simple reason why you start with a 50% answer. Why?
So that we can differentiate two elements. That we start with 50-50, but here we can't.
Well, there's two elements.
Yeah,
one side, the other
but
side.
we can differentiate that. So there is a difference between these.
Yes, there's a difference.
Yes.
Now, what's the probability that the heads will come up for on top?
Not 50-50.
Why not?
Because of the difference. Because of the physics involved there.
Yeah. Well, which one is it? Well, you gotta give me an estimate.
Difficult to say that.
Quite easy. The best estimate is 50% because there's symmetry involved.
There is no symmetry. Is it?
There is, because that could be heads, in which case it might have a higher probability of coming down on my hand because it lands smoothly.
Can I see,
Or that could be heads.
can I see that from here?
No, you can't. That's why it's 50%. It's because it's symmetrical and you don't know which is which.
Yeah. In that case, that is not is that to the battle?
No, I'm not saying the shape is symmetrical. I'm saying the state of your knowledge is symmetrical.
The state of the knowledge, yes.
Yeah. So anything that you say greater than 50% could be wrong. And if you're going to try to estimate the best error in terms of squared error, the best estimate of the probability in terms of squared error, then the middle is the best place.
The estimate based on the knowledge, yes.
Yes.
Based on the knowledge. Yes.
Okay. It's heads. Okay. This is exciting, isn't it? This is like gambling. Except you don't win. And neither do I, sadly. It's heads again. Okay, now what's the probability?
So I'd say exactly the same thing that I said before, but if that was like 50-50, so that doesn't change. Due to Gauss's fallacy,
Really?
yeah.
Do you know that this is biased? It's a bottle cap. So you said it wasn't symmetrical a little bit ago, and now you're insisting, it's heads again, by the way. Now you're insisting that in the presence of data, that you know nothing about what the bias is.
Okay, so here you're right, I agree. So here
It's
is...
so nice, he agrees after I argue.
So I'd say...
Makes me feel important.
So right now I'd say that if we have a lot of data right now, based on what you're showing, I'd be inclined to change. I'd be inclined to say something else rather than the original value.
It's heads again.
Okay.
How many is that? I can't count. That's why I'm a statistician. Whoops, I can't flip either. This is really scary this way. Heads again. Okay, now what would you estimate?
Right now I'd say... So
100%.
first, so what I
Would you do that? Would you take that? Okay, let's do this for money now. 100%. I'll let you soften that to 99%. Okay. You put you put 100 euros on the table. I'll put one because that makes it a fair bet based on your assumption there, right? If it's 99%, and I gave you the 99%, otherwise you'd have to put an infinite amount of euros on the table. You just put 100. I'll put one. If it comes up heads, you get my €1. If it comes up tails, I get your 100 euros. Are you willing to make that bet? No. So you don't think it's 99% even. You certainly don't think it's 100%. Okay.
165.
1.65?
0.65.
1.65. So he's gone up a little bit. Okay. Now, oh, that was a bad thing to do. Okay. It's tails this time. Okay, so it has some probability of coming up heads. And it's based on the data that we make this change in decision, right? We don't have this theoretical, well, some of us don't have this theoretical prior knowledge that it's exactly 50%. And so this evidence is a key thing there. And of course, we should remember the possibility that there's a third option, right? Which is it now? It's neither heads nor tails, it's gone. And so we should always have reserved a little epsilon in there for the man would cheat, right? Yeah. That's a good thing. But probability, as people express it, is a statement of knowledge. And here's a picture of your initial knowledge, as far as I can tell, right? Ain't? I don't know. That's the American form of it. It's an irregular verb. It could have been anything from 0 to 100. I mean, depends on the physics. And maybe if it fell a long way, it would always turn over and be like a shuttlecock. And maybe it would always go the other way, because maybe I put the heads on the other side in my arbitrariness. So it could have been almost anything. You probably guess it wasn't in the middle. You know, you might put a dip in the middle, but it would be a very broad distribution. And that would be based on your physics knowledge. And if you had none of that, you would just say this. Who knows? It could be 0 to 1. Now, if I flipped 5 heads out of 10 rows, I just destroyed the poor little microphone.
Try the other one again.
I'm going to just try not to stand right there.
No, it's the cable to the microphone there. I try to fix it.
They get better?
It should work.
Okay. It's the only cables I've ever had that would recover from convalescence. So 5 out of 10, we would say something kind of in the middle. We might be a little bit wrong. We have error bars there. We could express these by a nice probability distribution. This is a probability distribution of a probability. This is a thing that upsets some people. Somebody nervously laughs. I think they had a sad, frequentist childhood. Here's 2 heads out of 12 throws. And now we've pushed it a crazy. You know, this is symmetrical. This is like the probability of tails in our coin. It's the other way around. It could have been probability of heads over here, and so on. And if I asked you for one number, and I did, the real answer should have been, I don't want to give you one answer, but I think it's kind of at the low end. And we got a couple different answers there. If I ask you for one number that's going to be the best estimate in terms of squared error relative to the real probability, then we might give me the mean right there. But expressing one number for this whole distribution is a very bad thing to do. It gives some unrealistic feeling that we know something that we don't know. So we have to do something more. We have to at least put error bars on there. We say, it's kind of like in here. But it's kind of not like in there, because it could be here. It could be over there. It's not within the error bars. And if we make the error bars so big that we're certain it's within there, then we say 0 to 1, which is where we started. But we do have information. The only really good way to express what we really know there is to give that distribution. That is the state of our knowledge. And happily, that's not so hard. Which of these bottle caps? Well, practical physicist here. Okay. I bent it. So now you still don't know which one I was labeling heads and which one's tails, but you know these are probably kind of different, right? Now which one's the best? Do you want the one on the left hand or the one on the right hand?
From here I can see. I don't know.
You don't know. So you just try the left hand, huh? And then you might try the right hand, and you might try the left hand. And after a while you begin to get a feeling for one is better than the other, right? Yeah. So you try it a little bit, and you try different ones while you don't know. And here's the algorithm, which has been proven asymptotically optimal. And that is, instead of estimating the probability, sample the probability from that uncertainty graph, and then pretend it's the answer, and make your decision based on that. What that will do is we'll pick one of these according to the posterior probability that it is the best. Based on all the data you have, it will pick it according to the probability that it's the best. So if we've got enough data to say 90% for one, it'll pick that with 90% chance. If we have enough data to say, then, I mean, it's difficult to pronounce for non-English speakers, but that's okay. Then it would pick them with 50% probability. And the cool thing is it's asymptotically optimal. And if you put it against other options, popular thing like the epsilon greedy thing, it's up is bad. Up is regret. It's a sad word. But what it means is, what is the payoff, the average payoff that we got relative to the best. And however much worse than we picked. So if one of those is much worse than the other, and we pick it, then we have big regret. If one of them is equal to the best, well, one of them has to be equal to the best, and we pick the best, we have zero regret. And on average, as we learn more, the regret should decline if we're not idiots. And so it does decline in these two algorithms, but you can see the Bayesian band, and even with a very bad prior distribution, declines even faster than what is once, 6 years ago, claimed to be the best around. And in fact, it does very, very well. And here's a picture. I'm so sorry to everybody who was at Buzzwords, because they've already seen this movie. They know how it ends. Okay, so we have 5 coins here, not just 2. We have a red one. The red one's the best one. This horizontal axis in the top graph is the probability of success. Success is what we want. We want as many successes as possible. Red has about a half chance. Light green has a little bit less chance. Dark green has a considerably less chance. And purple sucks. It's bad. Okay? It's easy. And now the system has to pick which one to show. And because I made a mistake when I first rendered the graph, it's already sampled blue once. And it lost. Because it should. It's not a very good option. But that means that the posterior distribution for blue is canted toward losing a little. They could be very good. We just lost once. And the others all are on top of that and all sitting under the purple line and all losers. Now, this second panel is the probability that it's going to pick each one of those in the next trial. And the bottom panel is regret. So if we go forward a few steps, now purple has lost once, and light green now has been tried once and won once. Woo, that looks good. But even so, the sample of light green will be biased toward the right half, and the sample for purple will be biased to the left half, but they could be in the other order very easily. And so purple will still get some trials. If we go forward a little bit more, we see that it's giving light green a lot of bandwidth because it thinks it's kind of the best over here. And red in the middle there has had a few wins and a few losses, 2 and 2, I believe. And so it's completely symmetrical. It could be anywhere, but it's not 0 and it's not 1. And purple continues to lose. It has lost, looks like, 4 times out of 4 tries. It's a very sad coin. Green has lost fewer times, but only because it has been tried fewer times. And blue has actually won once, I think, out of 3 tries. So it's better than the losers, but not probably as good as the best. And if we look at these probabilities, light green is at the top, red is next, blue is down there in the middle, and purple is already almost eliminated. And by eliminating purple, we have decreased regret substantially. And I want you to learn. I'll let it run fast. And you can see the red and the green picking up which way to go. Red has overtaken green at this point, and the others are very much losses. We're not showing the bad options. So if these are recommenders, the bad versions are not being shown very much, which is okay because they're bad. And even if they were to agree on a result, they would all get credit. They would all learn from that same data. And so you can see red's coming way ahead here. Oops, green's coming up. There's a lot of stochastic variation. Red is getting more data than anybody else, so it's learning faster. You'll see the blue one, the scale is decreasing as the distributions get sharper. Blue ticks over a little bit every so often. We're giving essentially no data to purple and green. And now red is becoming quite narrow because it's getting lots of data. It's beginning to get a good estimate. And happily it's centered. The green one is still slightly optimistic. It's just luck of the draw. And over time, green will decline and regret will decline. So it's a nice, this is an online algorithm. And just like the other online algorithms we saw earlier, this one depends only on this algorithm that I'm not good at. It's called counting. But I can implement it on the computer. And you can see here red is now winning quite likely. And the probability that red is the winner is about 95% according to the system. And the regret is really tiny. So this is how a system can work. That's kind of cool to have an algorithm that just does that. Here's the code, in fact. The code above is the one that selects. You can see in a loop there it says R beta, that's samples from the beta distribution. And in the bottom, this is the learning. And here's the key code that does the learning. I hope you can read it, I hope you can understand it. K is K plus 1. That really is the learning there. This is cool, this is nice. The basic idea then is we can encode a distribution by sampling, and we can encode all the nuance of that distribution by sampling. And sampling allows unification of non-deterministic Bayesian computation and a very deterministic process like, did you click on the ad? Which one should I show? Which one should I show? Which algorithm should I pick? Now it can be extended. And the thing I just showed you is lovely and cool. It's not nearly good enough. Because we have convergence very fast with the two bandits, like the two bottle caps. It's pretty fast with the 5 that we saw there. But if we have 100,000, it's got to try all of the 100,000 to find out. I mean, the next one, the one next to one that I haven't seen yet could be the best. So it's got to keep going for at least hundreds of thousands of tries before it learns anything. And so when we have hundreds of thousands of options, and we do in this recommender system, because every one of those knobs, the size of the dither, the scale of the dither, the amount of the anti-flood, how many things constitutes a flood, all of those knobs exist, and the cross product of all of them is a huge number of options. We can't put a bandit at every possible setting of these knobs. Instead, what we have is some sort of parameter space, kind of like this, where we have theta 1, theta being a parameter that I don't want to name because I don't want to say what it really does. I just want to say a parameter. Theta 2 is another parameter, and the idea is that performance depends on both of them. Maybe it doesn't depend on one. Maybe we could adjust it any way we like. But the idea really is that we need to find the best of an infinite number of bandits that live in a space of knob settings. So now how do we do that? We have some model of click-through, which the probability of click depends on theta 1 and theta 2, which we don't know. We only have some distribution for them. And now we have some distribution for theta 1 and theta 2 that depends on our history, our historical evidence. And if we can adapt that, then we can sample theta 1 and theta 2, and then we can look at the different functions of those parameters to find the one that seems to be the best. So if we sample different theta 1s and theta 2s and sample those things, we can try to come up with a parameter setting which is apparently the best according to those samples. So we sample something behind the curtain and see which option in front of the curtain it would give us. It's just like the other algorithm, except for that one level of abstraction. One step back. Learn the parameter distributions from the past, sample the parameters, find out what the parameters mean by evaluating alternatives, F1, F2, F3, and then pick the best sample version. And then gather more data. That's the wrong slide. That was supposed to be the contact me slide. Anyway, the objective results are, the objective meta results are that this algorithm now dominates in ad selection. Google and Yahoo and Bing all use it. All of the independent folks that I know use some variation of this. It is easily the most effective known ad targeting algorithm. But it can be a meta-model learning algorithm too. We don't have to target ads with it. We can target which algorithm we're going to pick. We can target which knob settings we're going to use on a recommender engine. And we can optimize it. And that lets us then optimize over the space of knob settings without having to think about what those knob settings should be. Start them with some biased guess what it should be based on aesthetic considerations, put a wide uncertainty on it, and let it rip. And that's how I think we ought to build recommendation machines. And I will go back to the contact slide. So if you want more information about this, If you want the code's on GitHub, not for recommendation meta modeling, but for a simpler task. You can adapt it, you can have it, send me an email, or send me a question, or hop onto the Mahout mailing list. Let's talk. Any questions? Pummel you.
I would say thank you very much.
Okay.
That was very fun.
Okay. Yeah.
So sometimes users click on, let's say, free results. So if you use click-through rate as feedback mechanism, or it as feedback mechanism, sometimes users do not indicate success, rather the opposite.
Yeah, so he says click-through rate is a very dangerous thing. And he used a different example, but it's absolutely true. The only reason I wrote click-through rate there is because I decided to redo all my slides while the first guy was talking, and so I just had to put something down very quickly. In fact, click-through rate is a horrible choice because what that does is you optimize for spam. The thing that has the most attractive title, people click on and then they go, because it's misleading. And we saw this very, very much in video, where pirates would put pirate videos onto our site, and they would say, pictures of mother gardening with the cat. And it was really Iron Man 3, that sort of thing. And then on their site, they would say, Iron Man 3, Part 2, go here. And so people would search Google, find that link, come to our site. We would give credit for people coming out of nowhere. Mother is a very interesting person, apparently, so we would say most popular. And people look at that and they say, that's bullshit. Why do I want to see that? That's on the most popular page. But if we saw people come and then search, say Iron Man, and then they would disappear for a while, and then come back and they'd watch Mother Garden, we would see that correlation. But what we would see would be a correlation between typing the words Iron Man and engagement with the video. Not clicking on the link, but engagement. Watch 30 seconds. It's very, very important to have some sort of surrogate for happiness, happy user, that you can understand quickly. But it really has to be a surrogate for happiness and success, not something subject to spamminess. Because other people would put videos that say Iron Man Part 3, and it would be their mother gardening, because they're just idiots. And so those people get a lot of clicks, and we would piss off a lot of users. So what you said is exactly right. What I typed was, I'm a fool for redoing all my slides. But yes, the point really is that I meant as a metaphor, click-through should be for success. We should pick a good surrogate for what really is making things better. It isn't just clicking. It isn't just views. Netflix in the US has switched over to an autoplay mechanism where you hit the end of a video and it plays the next video. I continue to sleep. It plays the next video. It's increased usership. Isn't this awesome? No, it hasn't. It's increased the amount of time it flickers in front of my face as I sleep.
It makes people sleep.
No, it doesn't make you sleep anymore. The first one puts you to sleep.
Yes, the first one's not good.
Yeah, the second and third just increase their costs. And so that's a good example of optimization in a silly way. And really good companies understand that there's something deeper about this. And so I deal with a very large bank whose name you would all recognize, and they don't let you recognize it. And they, when I talk to them about how do you pick which thing to send people, they say, well, it's very hard because we don't want to just send them what they will do right now. We want to send them things that establish a better relationship between us and the customer. And I say, well, how do you measure that? And they go, that's hard. And they start talking about over a period of years, this sort of thing. And so they don't have a fast surrogate there. And they are very, very focused on what makes people happier and better relationship with the bank. And some banks don't care. They just say, hey, we knock the fraud down, get people to transact, we're good. It's not what makes value. I mean, this one company that I'm talking about, they charge you a lot of money every year, $400 for their card. So they better make you very $400 and $5 more happy every year. And so but they do it. They've been doing that sort of customer relationship for 160 years. So they clearly do something well, but they very much understand this idea of the good surrogate and the bad surrogate. More questions? Yeah.
How do you tackle the non-stationarity problem?
How do I detect non-stationarity? Well, it's an interesting problem. So there's two answers to that. One is from the recommendation engine part. And the way that the computation is done offline and online, the offline part is very, very stable based on observations. Relationships between content items, between products, are fairly stable. Now, you may filter them according to whether or not you have any of those things to sell. But the relationship between those is a pretty stable thing. You know, terrible movies of a certain action sort with superheroes in them, we think are quite similar. And it's not going to be tomorrow that all of the great literary works of the universe are highly related to those. It just doesn't change. Pride and Prejudice is related to Persuasion, and maybe Thomas Mann, if you're multinational, and Iron Man is related to Spider-Man. Ish. But you see what I mean? So some things are very stable.
Yeah, but we usually estimate this relationship between these items based on user behavior, and that user behavior changes, we might need to change the item relationship.
Yeah, it does change, but it doesn't change that much, and people have certain mixtures, they change very slowly, and if you have any kind of time window on that, you find out that at a time when somebody was very juvenile, the juvenile things that they like are related. When they become much more mature in their tastes, that doesn't change their relationship with juvenile items to each other. It changes the relationship of that user to juvenile items. And we use the recent history to decide what to recommend to this user. The recent history is mature tastes, and their past history, so at the time they were being a juvenile, we give them juvenilia. Now we give them much more mature material. So that the time for what you like right now is based in the history that we give to the offline product. But the offline product itself is quite stable. So we segregate these things into slow and fast parts. And we can now give you long and short recommendations. The shortest recommendation, if you go to YouTube, the bottom of the thing, there's related videos. That's a very short recommendation. It's given that you've watched this, here's what we think you should see. When you go to your personal favorites page, it's going to give you much longer term recommendations. So, we can change that just by how much history do we give and how do we rate that. But the relationships don't change. That's part of the answer. It's not, I think, what you're asking. What I think you really wanted to know is how do we decide on non-stationarity on Bayesian bandits themselves? There's several mechanisms. One is that the counts can have decay. It could be exponential, it could be boxcar, it could be sums and differences of exponentials to give things that go smoothly off after a period of time. There's lots of ways to do that. That's easy. We can also run short and long models, and then we can put a meta model on top of those. And the model, each one of those is looking at hundreds of thousands of options and learning. And the meta model can be learning, is the wise old Bayesian bandit better, or is the young and foolish one better? And we can put a medium time length on that one. And if it suddenly starts giving weight to the young and foolish, we know the universe has changed. So we can do those sorts of things. And that's useful not so much in recommendations, because recommendations don't change so much like that, but it's very useful in financial time series, where the world does change in 2008, 1929, those times. The world really changes. People's attitudes change. How much money they spend changes. Whether or not they will give loans changes. All of the fundamentals, all of the constants of business change in those moments. And long-term models become they become pessimizing models. They become ways of